Hey guys, welcome to our 14-point extension lesson. It's called extension because this is not in the book. So there's a handout on Google Classroom that you should print out before you continue watching this video so that you can fill it out as you're watching the video. You'll see that your homework will also be a worksheet, and the worksheet and answer key will be available to you as well. So today we're going to look at the graphs of cosecant, secant, and cotangent, the other three trig functions we haven't looked at yet. And we'll be doing a bit of modification with them as well. We won't do all the transformations that we did for sine, cosine, and tangent, but we'll do some of them just to give you a flavor of what they look like. We're going to start with cosecant first. And for cosecant, basically, the key here is to remember that cosecant is the reciprocal of sine, which means that we can use the values for the sine graph to create the graph of the cosecant graph. And typically what we're going to do is we're actually going to graph them together using different colors. And generally, especially once you get good at this, you'll only need to graph the 5 critical points for sine in order to create the cosecant graph. We'll start though by actually doing the curves for both so you can see how that looks. But you may get to the point on your homework where you just need the 5 key points for sine. So let's start by taking a look at our sort of what I call our discovery sheet, where you can fill out the table, plot the points, and see what a cycle of cosecant would actually look like. So I'd like you to take a moment where you pause the video, you fill out the rest of the table with the decimal values for cosecant as the reciprocal of the sine values. And then you plot all the points for both sine and cosecant. So I want you to plot both in 2 different colors on your graph. And then once you've done that, you can resume the video. All right, so just to take a look at this table a little bit here, one thing to notice is that anytime sine is 0, the reciprocal is going to be undefined. So you should have undefined listed in the 0 spots. And obviously your table is fully filled out. I'm just going to fill out a few of these values just so that as we're kind of going through this, we can take a look at these together. And you'll notice that I'm highlighting in particular the 5 key points that we use for sine. So I'm going to start by plotting our sine function first. So we would be at 0, 0, and then at 90 degrees, we're at 1, and then back to 0, and then down to -1, and then back to 0 again. So if I draw in my sine curve here, that'll help us to see our cosecant curve. Because the first thing to notice is anywhere where you see undefined, for cosecant, so I'm going to do, so blue is going to be sine, and red is cosecant. So anywhere where we had a 0 for cosecant, that's going to become a vertical asymptote. And then our 1 and -1, the reciprocal of 1 and -1 is obviously the same. And then what you'll notice as you plotted these points, you probably noticed that your points tended to trend up and away towards the vertical asymptotes. And if you look at this, you'll see that essentially it's symmetrical along a line at 1, or for the negative version, it's symmetrical along a line at y equals -1. So in other words, the sine function, as the sine function goes to 0, the cosecant function goes to infinity. And that's the same thing except towards -infinity along the bottom. So the one cycle of the cosecant function essentially mirrors in sort of a reverse way one cycle of the sine function, which means that our period is going to be the same as sine. So our period is 2 pi or 360 degrees. And in this case, our amplitude of the cosecant function defaults to 1, but the amplitude isn't the distance from the middle to the peak or trough anymore. Instead, the amplitude reflects where the vertex of each of those curves exists. So let's take a look at a couple examples here. So on your handout, I want you to skip the discovering page for cotangent for a moment and go to example 1 on your handout, because we're going to look a little bit at modifiers, and we're going to look at secant, which operates much the same as cosecant, except secant is the reciprocal of sine instead. Or I mean of cosine, I'm sorry. So in this case, if we look at this one, our amplitude is 2, because that's the value before the secant. We don't have any phase shifts, either vertically or horizontally. And in this case, our period is going to be 2 pi over 1/2, which equals 4 pi. So the way I'm going to graph this is I'm going to start by first graphing the cosine graph. But we're just going to do the 5 key points for cosine. So we'll put in our amplitude at +2 and -2. And our midline is going to be at 0 because there's no shifts. So in this case, cosine, we'll put in our 5 points as well here. So we're going to start at 0, and we're dividing 4 pi rather than 2 pi. So our middle would be 2 pi, and then we have pi and 3 pi as well. So for cosine, we start high, and then go to the middle, and then the bottom, and then back to high again. So our cosine function would look like this. So what that means, now we can put in our secant function. And for secant, the key again is we have vertical asymptotes everywhere where we had a 0 value, because the reciprocal of 0 is undefined. And then we're going to have our points, our vertex points will be at the peak at bottom of the cosine graph. So then our secant function, one cycle of it, just sort of mirrors the cosine function in the opposite direction. So that would be, the red is one cycle of the secant function. So let's try another example, and I would like you to try number 2 on your own. So I'd like you to pause the video and see if you can do this cosecant example. Graph the 5 key points for sine first, and then try the cosecant, and then resume the video as soon as you're ready. All right, so I'm going to start with sine first. And here I'm going to notice that my amplitude is 3, and I'm also just going to make a note that it's reflected as well. I don't have any shifts again. And my period here is 2 pi over 2 pi, which means our period is actually 1 in radians. So I'm going to start with putting in my amplitude marks. And then for sine, then I guess I'll put in my 5 points as well here and label them. And make sure that you're doing that as well. You should always label your horizontal distances. So we know we're going from 0 to 1. So our middle is going to be at 1/2, and then we're at 1/4 and 3/4. So sine starts at 0. In this case, we're going to go down to -3 because it's reflected, and then back to 0, and then back up to +3, and back to 0. So this is our sine function in this case. So now we can go ahead and draw in our cosecant function. And for the cosecant function, we'll put in our vertical asymptotes first. And then all we need to do is mimic the sine function in the opposite direction. So we've done cosecant and secant at this point. Now we're going to look at cotangent next. So go back in your handout to the Discovering Cotangent page. And I'd like you to do the same thing. I would like you to make sure that you plot both, we're going to plot tangent as well as cotangent in two different colors. So you're going to pause the video, you're going to fill out the table, and then you're going to plot all the points for tangent and cotangent so you can compare how they are the same and how they are different as well. All right, so I'm going to start with tangent first. And tangent is one that we already have explored before. So we know that there is a vertical asymptote at 90 degrees because sine is 1 and cosine is 0. So it's undefined because tangent is sine over cosine. And there's also going to be a vertical asymptote at 270 degrees as well. And then when we go to draw on our tangent, we have a point at 1, as well as at -1, 0, and 1. So my tangent function is going to look essentially like this. And we just need to finish this off here. So this is our tangent function. So then our cotangent function is essentially just the reciprocal of the tangent function. So if we look again at our 5 key points here, everywhere we see a 0 for tangent, that means that we're going to have a vertical asymptote. Where we have an undefined for tangent, we're going to have a 0 for cotangent because it's the reciprocal. And that would be 5 key points, remembering that when we do our 5 key points, tangent only has a period of 180 degrees. So I've actually drawn on here 2 cycles of tangent, and I'm going to draw in 2 cycles of cotangent as well, just so you can kind of see how this looks. So for cotangent, we will have our vertical asymptotes at 0 and 180 degrees, and then also at 360 degrees. And then we have a point at 1 and -1 and 0. And so our line comes in the opposite direction of tangent, which makes sense because it's the reciprocal again. And so then we've got the same thing where we can put in our points again for a second cycle of cotangent and see how that looks as well. So as a reminder, the cotangent period is pi or 360 degrees. The default amplitude is 1, but remember that the amplitude is just reflecting kind of where those intermediate points go. So let's try the last example here. So you'll flip back to the last example in your handout. We're going to look at one with just a little bit of modifier. So we're going to do the cotangent of 3 pi. And so, again, if we approach this, the key here is our amplitude is 1. Our period is pi, not 2 pi, pi over 3. We didn't include any shifts for this one. So in this case, we know when you look at the cotangent vertical asymptotes, unlike tangent, where the vertical asymptote is in the middle of the cycle, for cotangent, the vertical asymptotes are at the 2 ends of the cycle. And in this case, our points here would be at 0 and pi over 3. So then in the middle, we're going to be at pi over 6, and then pi over 12, and here we'd be at pi over 4. So in this case, we're basically looking at our 5 key points, and the cotangent function is always going to, so we need to include our amplitude at 1 and -1, and it always descends unless it's reflected. So our cotangent function would look like this, and that would be 1 cycle of cotangent. So these can be a little bit tricky because there's just a lot more to visualize when you're thinking through these problems. Remember that you can always think through the values on the unit circle to help you think about these problems as well. But this brings us to the end of our video. The homework again is a worksheet, and the worksheet and the answer key are available for you. Let me know if you have questions.